So guys, welcome everyone. Let's start our last seminar from this year, from our community. Felipe Navarete will talk about high mass star formation. If you have any questions on YouTube, please use the chat as the last time, or here, just ask. Okay.
Okay.
Well, Felipe.
I hope you all can hear me. Can you hear me in the audience as well? Okay, so welcome everyone. My name is Felipe Navarete. I'm from the Department of Astronomy here in the University of São Paulo. And today I will talk about height mass star formation at gigahertz and terahertz frequencies, thinking on the upcoming facilities that will be available for the Brazilian community as well, like LLAMA, for instance. So this is the outline of my presentation. First, I will talk briefly about height mass star formation, the theory and the observations behind it. Some synergy with infrared and submillimeter surveys that are available. Some of my ongoing works, CO observations at the Apex telescope, which is a twin telescope of the LLAMA, and some works on molecular outflows. Then I will move to some perspectives and future works, for example, with LLAMA and other facilities. And finally, I will give you a brief summary of this presentation. So whenever we are talking about high mass stars, we are talking about stars with 8 or more solar masses, stars with stellar type higher than B3 in the main sequence or earlier. These sources are really bright. They have bolometric luminosity larger than 10 to 4 solar luminosities, and they are extremely rare in the universe. So they correspond about 1% of the stellar population of our galaxy, for example. And finally, and not more, they produce all the heavy elements in the universe, and they rule the evolution of the interstellar medium, ISM, and the galaxies. So whenever we are looking for those objects, we have to go for longer wavelengths. Why? Because high mass stars are often located in the densest regions of the molecular clouds. So we have a well correlation between high mass star forming regions and the emission from dust. So in this figure, for example, we see the two regions that form high mass stars in blue. Blue is the emission at 10 microns from the MSX images. And superposed, we have these images in red, corresponding to the emission from the dust at 870 microns from the Atlas Gal. So whenever you are looking for high mass star forming regions, you have to take care and to care about the dust. So I said that high mass stars are extremely rare. So how many stars are there in the universe, for example? If we take a population of 1,000 of stars formed in the Milky Way, our galaxy, and we take an initial mass function, for example, the Krupa 2001, you have some distribution like this. So this is the amount of stars, and this is the mass of the stars. So here we have three separations, 0.08 solar masses, 1 solar masses, and 8 solar masses. We are interested in this side of the IMF. So for every 1,000 of stars, we have 350 stars that are brown dwarfs. They have 0.08 solar masses or less masses than that. About 585 are low mass stars. They have less than 1 solar mass. 60 have intermediate masses, so between 1 and 8, and only 5 of 1,000 are indeed high mass stars. So yeah. To talk about the theory of high mass star formation, we first have to take a look on how low mass stars are formed in the universe. So Xu and collaborators in '87, they proposed a disk-mediated accretion scenario to explain the formation of these objects. So we start with a molecular cloud, a dense molecular cloud. Then we have instabilities here that leads to gravitational collapse of this cloud. The mass accreted into the center of this object forms a disk, and the material then is folded into a disk, and the material that's not accreted into the central star is ejected in the form of bipolar outflows. So in the end, we have a protoplanetary disk, bipolar outflows, and a central star that has been formed. So in this scenario, we have the gravitational collapse, we have the angular momentum conservation that leads to the formation of the disk, and we have the circumstellar disk and collimated jets. That's what we observe in the universe in low mass stars. If we take this model, if we scale this model to high mass stars, we have to deal with another ingredient that is the radiation pressure. Back, I think 10 years ago, we were still dealing with this, and people were saying that we cannot form stars more massive than 40 solar masses due to the radiation pressure. The radiation pressure would dissipate the disk, and then you cannot form stars heavier than 40 solar masses. However, in 2009, Krumholtz performed an MHD simulation of a 100 solar masses clump. Oh, where is it? Yeah. Assuming the accretion scenario from Xu, including radiation pressure in this simulation. So I will just show you what it is about. So in this side, we have the face view of the simulation, and this is the edge-on view. So here we can see the system. So you have the collapse here in the center, and then you form a disk-like structure. And this is the radiation pressure acting. So by the end of the simulation, you are not forming a single star, but you form more than one star. You form a binary system. In this simulation, for instance, you have a circumstellar structure here that is associated with the formation of the massive star. And you also have the coalescence of smaller objects. So you have the formation of smaller stars that are accreted into the larger ones. So this model was proposed by Bonnell in 1998. And this model alone cannot predict the formation of all stars in the universe, but it is present in the formation of assuming the circumstellar accretion model. So by the end of the simulation, from 100 of stellar masses, we have a binary system with 40 and 30 solar masses. So this model proves that you can indeed form massive stars with this scenario. So, okay, we have the model, and now we have the observations. What kind of observations can we perform to observe the stages of high mass star formation before the main sequence? So this is a scheme proposed by Cormac Purcell. It shows a large clump of cold matter, and then some stages of evolution of high mass stars. So this is the sequence of the evolution of a high mass star. And let's start with the filament, for example, this structure here. what we observe in the universe, thanks to Herschel, now we can see this kind of structures in the far infrared, closer to the submillimeter, and you see such bright and beautiful structures like this one. It has 85 parsecs at a distance of 5.5 kiloparsecs. So in the brightest regions, brightest spots of this filament is where you expect that the star-forming regions are ongoing. The star-forming process is ongoing. So by following, you have a cold collapsing core. So what are the evidences for collapsing cores that we have in the literature? We have this kind of profile of some molecules. So this is the scheme proposed to explain this double-peaked profile. You have velocity gradient from the outer edge to the inner region of the region, and then these velocity gradients produce two peaks. The blue is brighter than the red. I'm sorry about this feature here. And you have a self-absorption in the center of the profile. So very often we observe this kind of profiles in several molecular transitions in the radio, for instance. So moving on. Okay, how is the spectral energy distribution of this kind of sources? We are still in the first part here, in the first stage. So this is the spectral energy distribution of one typical cold core. This is the flux density, and this is the wavelength, so it grows to the right. So here we have a very far infrared weak source. So it has only fluxes in the far infrared, and then you as the clump starts to evolve, you start to see the near and the mid-infrared flux of these objects. So moving on, then we have the last stages, where you expect that most of the accretion is going on. You have the circumstellar disk feeding the central source. You have the jets associated with the star-forming activity. And after that, you have the star that the radiation field is already sufficient to ionize the surrounding ISM. So again, this is the spectral energy distribution of sources at these stages. So here we start to see the infrared emission of the source, and here you need two components of black body to fit the spectrum. You need a component for the dust at longer wavelength, and another component for the infrared emission that's supposed to arise from the star. So whenever you're looking at those later stages, you are dealing with H2 regions already, and then you see that the flux at the infrared increases, and also you start to see emission at the centimeter wavelength. Okay, what are the observables that corroborates with such classification? Thinking about molecular outflows, we have emission of SEIO. So you see several transitions of SEIO along the spectrum. And this, for example, is the 2 to 1 transition and the 3 to 2. The blue lobe of the outflow and the red lobe of the outflow can be seen as a wing in the blue and a wing in the red side of the spectrum of the SIO. And you can also derive the parameters of the outflow by investigating these lines and maps of those profiles. And how do you know that you already have an H2 associated to the star? you have to look at the centimeter continuum emission of the source. For example, at 6 centimeter, you have several different kind of structures associated to H2 regions, either in the ultra-compact H2 region, hyper-compact, or an H2 region, a giant H2 region, and thereon. So whenever you detect centimeter continuum emission, you are dealing with a more evolved Pramen sequence star. Okay, how is the flux distributed along the spectrum in high mass star forming regions? If we take, for example, the SED of this source, which is an H2 region, so it's an evolved system, we can have the SED fitted by two components. It's a gray body component fitting, and we have the fluxes for every flux here was extracted from available data in the literature. If we start from the larger wavelengths, we are dealing with La Boca emission at 870 microns. And this emission has temperatures typical of 3 Kelvin, for example. And then if you move to the far infrared, we have the emission from the Herschel Spire instrument at 360 micrometers. And then you are dealing with emission at 8 Kelvin. So this is not the image of the Spire, I'm sorry, it was the last one. But moving on, then you move to the 100 micron emission. Then you have the emission arising from 70 microns. This is the warm dust around the system. Then here you start to see very bright sources associated with the extended emission. Moving on, we're now at 20 microns. We have maps of the WISE catalog from the Spitzer Space Telescope. And here, again, you see very bright structures and saturated structures at the center. And here the dust is at 105 Kelvin, for example. Excuse me.
I'm not sure I agree with this translation into temperatures, because there's a
Can you say here because of people on YouTube?
Yeah.
There's a single black body.
Yes.
You're probing at different wavelengths.
Yes.
So if you're pointing out emission in different spatial locations, I may agree with you. But if you're talking about the same region,
Yeah, you're right. Let me explain better. This is just the Wien approximation of the peak temperature at this frequency or wavelength. Sorry. Yeah, you're completely right.
the brightness temperature.
Yeah. The brightness temperature. Yeah. So moving on. We have the IRAC Spitzer at 4 microns, and then here you start to see the stellar population in blue, and the warm, the hot dust, for example. The typical temperature in this case is about 700 Kelvin, and if you go to 2 microns, it's not here in the plot, but you still can have these maps. You only see the stellar population of this region. And here, the brightness temperature is about 1,030 and 300 Kelvin. So, when we look across the spectrum, you have to ask at which wavelength range should we look for the precursors of high mass stars. It will depend on the evolutionary stage of the clump of the source. For example, if you want to study earlier stages of the high mass star formation, they are indeed brighter at longer wavelength. So it's better to use like longer wavelengths to start looking for the sources you are interested in. So I told you about the spectral energy distribution across the spectrum. And now we can talk about the synergy between high mass star formation and synergies with available and ongoing surveys. I list here four sources that I use the most. So they are galactic planning surveys looking for precursors of high-mass stars. So the completed surveys are two. One in the mid-infrared, it's the Red MSX survey from Lumsden 2013, and one in the sub-millimeter, which is the Atlas Gal from Schuller 2009. And there are two ongoing surveys, which is the SEDGISM, which is an upgrade of the Atlas Gal survey. It is based on molecular line observations, so it's mapping the whole sky on molecular lines. And another one at the far infrared, it's the Height-Gal survey, the Herschel Galactic Plane survey. So the RMS, it contains at least 2,000 high-mass young stellar objects distributed in the galactic plane. So the main idea was to take observations of the whole galactic plane to identify the most complete census of sample of high-mass young stellar objects and H2 regions using the mid-infrared. They made some additional follow-up observations in order to exclude other objects with similar colors than those objects here. So in addition, this survey provides a list of protoplanetary nebula and evolved star that have mid-infrared colors similar to ISOs and H2 regions. So whenever you're looking for, you're studying one of these objects, you can also use the RMS for this, using this link here. And this is the distribution of the sources. In blue, you have the high-mass stars. In red is the rejected sources. And the lines correspond to the fitting of the spiral arms. So yeah, here it's in the north, and this is the distribution in the northern galactic plane. So, and then we can talk about the Atlas Gal and the distribution of the dust. So the Atlas Gal is the apex telescope large area survey of the galaxy. So the aim of this source is based in whatever you want to find star-forming regions, you have to look towards high column density regions. And these regions here are very bright at sub-millimeter frequencies. So this is one example of the galactic center at 870 microns using the La Boca instrument of the apex. Those observations have angular resolution of around 20 arcminutes and sensitivity to 60 millijunks per beam. This is quite an improvement. Okay, the Atlas Gal observed the inner galactic plane. So this region here from -60 to +60 degrees. And it provides a full coverage of precursors of high-mass stars in this region, the inner galaxy. So, if you look to for the structure of the dust that Atlas Gal has you can find diffuse emission at that wavelength. You can find filaments, such as this one, and you can also find clumps, which are very compact sources. So, the clumps are...
No, the whole.
Oh, okay. This...
I cannot read.
Yeah, me neither. It's about 0.1 degrees, this. So, yeah. I'm sorry, this, yeah. Okay, so basing on the detection of the clumps, the Atlas Gal has two main catalogs, the CSI, with about 6,600 compact sources, detected above a 6 sigma threshold, and the GCSI with 10,000 compact sources. So those clumps are expected to be the earliest stages of the high mass star forming regions. So if you're looking for those objects, this is the kind of precursors you have to focus on. Okay, then we have now an upgrade of the Atlas Gal. It's the SEDGISM, Structure, Excitation, and Dynamics of the Intergalactic Interstellar Medium. The idea of the SEDGISM is to take the southern inner galaxy plane and observe it between 270 to 221 gigahertz. In these regions, we have lots of molecular lines of interest. And this is one example of the fields they observed. This is 13 CO221 observations at 2 velocity ranges, so minus 51 to minus 43, and minus 96 to minus 90. So the goals of the SEDGISM then is to understand the large-scale structure of the interstellar galactic interstellar medium, the origin and life cycle of molecular clouds, and the process in the interstellar medium that controls the star formation. Okay, this is one of the schemes that shows the lines that are aimed, that are being observed by the SEDGISM. You have SIO lines, you have molecular lines, methanol lines, SO2, two isotopologues of the CO221 lines, and SO. So you have a plenty of lines that will be observed. So it will be a huge data cube. This is one example of the fields they observed with the position of the lines as well. And this is the example of the lines in one of the another field they observe. So those lines are detected with relatively high signal to noise, and you can make science out of this. So finally, we have the last survey. It's the HIGAL, the Herschel Infrared Galactic Plane Survey. It's well described in Molinari 2016. And they observed the whole galactic plane from -1 to +1 latitudes in 5 bands between 60 and 600 microns, with spatial resolution from 4 to 40 arcseconds. So the HIGAL is aiming to provide a complete sense of star-forming regions and cold interstellar medium structures in the galactic plane. And one thing is that they plan to provide all images and catalog to be public available. This is one of the fields, the testing fields they observed. So in blue, we have 70 micron emission. In green, we have 160 micron emission. And in red, we have 250 microns emission. So this is the region of the galaxy they are aiming. So they will have a completely census of all star-forming regions within this region of the galaxy. And this is just the comparison with previous surveys with similar objectives. So then the science done so far with, for instance, the Apex telescope and the Atlas Gal survey. So the Atlas Gal, the initial catalog of the Atlas Gal, we have 10,000 of sources, and then we selected a sample of the hundreds brightest Atlas Gal clumps selected from the survey, with additional infrared criteria in order that we can separate them into the classifications of the main sequence phases. So the idea here is to identify a solid evolutionary sequence for high master formation through observations of CO, other molecular lines, radial recombination lines, and the ionized gas. We can also observe warming up of the gas as a feedback process from the central sources. It's a published work from Gianetti 2017. And here I will focus on two works, the characterization of the CO emission, the 12 CO emission, and the association of the Atlas Gal top 100 sample with mid-J CO outflows. So, to talk about the observations, it's interesting to show what kind of instrument APEX have to think about the future of our community, for example. So the first instrument I used there was the FLASH, First Light Apex sub-millimeter heterodyne receiver. It's a dual band receiver. It observes two frequency ranges between 350 and 460 gigahertz. So you can observe simultaneously on these two bands. And in this situation, we observed two transitions of the CO, the 3-2 that was not used, and the 4-3. The single pointing observations have beam sizes ranging from 13 to 18 arc seconds. And the other instrument that we used was the carbon heterodyne array of the Max Planck Institute for Radio Astronomy, the CHAMP Plus instrument, that also observes simultaneously two bands in the sub-millimeter range, the 60 and the 660 and 850 gigahertz. The difference between CHAMP and FLASH is that CHAMP Plus have two sets of 7-pixel arrays, so it's a camera distributed like this. You have 7 pointings taken at once in each of these two bands. So it's ideal for performing on-the-fly maps, for example, for mapping regions in the sky. So with this instrument, we observed the CO625 and the CO726 lines. And the beam size here were about 8 to 10 microns. This is a very important thing because as far as I remember, the CO625 will be the only CO transition available during the LLAMA first light. So if one wants to study CO, it has to focus on the CO625. And okay, so this is just a brief summary of the observations. We have CO423, 625, and 726. And all our spectra was convolved to the same resolution of 13.4, which was the resolution of the single pointing CO423 observations. And also, they are shown here. And also we have integrated maps of the CO625. This is the transition that have the higher signal-to-noise ratio among the two mid-JCO lines. So we focused on the structure of the CO625. From the integrated intensity of these profiles, we can investigate the CO line luminosity. So it's the flux corrected by the distance of the source and the beam dilution. And also we can compute the CO line and compare with the bolometric luminosity of our sources. So at first we find a very good correlation between these quantities. And one thing that must take care is that we have several cases of self-absorbed profiles in the sample. And those sources flagged with in yellow are are self-absorption free sources. So they also follow the same trend we found for the whole sample. So the self-absorption is not introducing any bias in the analysis. We can do this, okay, this is what we find. The strength of the CO increases towards more luminous and more evolved clumps. And we performed the same study with the other two CO lines, and then we find steeper relations, for instance, from the CO423 to the CO726. Those are, okay, this relation gets steeper with the J number of the CO transition. And this is an interesting fact. So by taking that in mind, we now can plot the power law index of the slope of that relations as a function of the J, the upper J level of the transition. For example, this is the power law index of the CO423, and then to the 726. And also we can include this one slope from the CO 10 to 4, 10 to 9 from another work. And we find that the roof follows a linear trend. So we can say that we have now a CO ruler that you are able to predict the CO flux at any frequency based on the luminosity bolometric of your source. So it's a good relation that we have here that can be tested in the future. It has not been tested yet. Okay, then using the CO625 maps, we investigated the wings of the emissions. So this is the wing of one of the clumps. This is the spatial distribution of this emission. Then we integrated the red wing of the emission, and we find another distribution. So this is ideally the outflows driven by these clumps. Then with these maps, we can construct maps of the blue lobe and the red lobe of the outflows, and then derive the properties of these outflows. Then we can also compare the presence of outflows with other tracers, such as those probed by the IRAC-Spitzer maps. This RGB maps shows in red the 4.6 micron emission of the IRAC instrument. And in 4.6 microns, we have a transition of the H2 line, which is also tracing. It's associated with the extremely green objects, which is associated with outflows from the past decades. So we find very good correlation between the presence of CO outflows with these EGOs in these cases. And also we detected outflows in 85% of the top 100 sample. So CO outflows are very common in these objects. Then we derived the physical parameters of these outflows based on the integrated flux. So we derived the total column density, assuming an excitation temperature of 65 Kelvin, and assuming the integrated emission of each, the red and the blue wing. And then we computed the mass of the outflow, the total mass of the blue and the red wing. The importance to compute the outflow parameters is then to compare with the bolometric luminosity of the clumps, for example. So we can see if there is some relations between the parameters of the outflow and the clump. In this case, we show the mass entrained by the outflow and the bolometric luminosity of the clump. And again, we find a very good correlation between these two quantities. In red, in purple, we show two trends that has almost the same slope as we derived for our relation, but are offset by 2 orders of magnitude. And they studied similar sources as us, than us. Okay, the red one was observed by Wu 2004 in the CO's 2-to-1 transition, and they observed 400 sources. The purple one is from the CO's 3-to-2 transition, and okay, it's quite the same luminosity range of our sources. We still don't know how to explain this offset in the mass entrained by the outflows, but we are trying to work on that. We also probe that the entrained mass of the outflows are correlated with the mass of the clumps. So we see that this property of the outflow is very correlated with the property of the main source. Okay, we also, oh, this is very low quality image, sorry for that. So in this plot we show the mass loss rate of the outflow, the force of the outflow, the dynamical force of the outflow, and the luminosity of the outflow. We find very good correlations as well between these quantities and the clump properties. So, did you raise your hand? No, okay. Okay. We also find that these results are in agreement with our previous works. For example, from Aud 2015 and from Wu 2010. Okay. Now we can talk about perspectives on future works at these frequencies, gigahertz and terahertz frequencies. Starting from ongoing works, we have one ALMA project, fully observed now. It's a band 6 ALMA observation that we were aiming to investigate the launching point of the outflows that we detected with the Apex telescope. These are some examples of the outflows that we observed with ALMA. And the data is still being analyzed, so I don't have access to it. But yeah, this is one thing that's going on right now. And we can also think on comparing the emission from the outflows at different wavelengths. For example, in these plots, we have the maps showing the near-infrared H2 line at 2.20 at 12 micron, which is tracing jets from massive stars, overlaid by the CO outflows. So we can also investigate whether the jets and the outflows coexist, or one is driven by the other. In this work from Sana 2016, they ask who comes first, the jet or the outflow. So this is a very important work that we can still do with the already taken data we have. And we also can study the astrochemistry of the outflow using single dish antenna as a function of the evolution of the clumps. We can, for example, investigate broadband spectra of many molecular features, SIO, CS, H2, HCO+, using the LLAMA telescope when it will be available. We can talk also about filaments, which are the major structures related to star formation regions. So they are structures associated with dense and cold gas. They are large reservoirs of mass from large to small scale. So they represent an inflow. So you have inflow movement, inflow process from in the filaments. And we have evidence of gases streaming, inflowing into small scales on protostars. So the question is, are the protostars being fed by material from the filaments or not? So in this example, we have the observations of this filament at different wavelengths in the far infrared. So in the Spitzer, it appears as a absorption feature. If I take this off, okay, then here again it's an absorption feature, but here you can also see the star-forming regions in emission. But as soon as you go to the far infrared, these structures are really, really bright. So yeah, and thinking about the inflow and outflow activity, we can also think if the outflows are aligned or not with the filaments. So, as I said, you can investigate the filaments using IRAC Spitzer maps at 8 microns, shown in green here, and the CO outflows, maps that we already have, are shown in red and blue. And then you have a proposition, or those contours are just to highlight the position of the filaments. Then we have a proposition that inflow motions, inflow process are aligned with the large-scale filaments. And therefore, if the inflowing material on the protostars are aligned, the disks should be aligned with the filaments. Therefore, we expect that the outflow gas must be perpendicularly oriented to the filaments, or exhibit some situation like this. You cannot have filaments and outflow aligned. They should be counter-aligned, for example. Perpendicular, sorry. This is something that we can understand, we can study right now with the available data we have. And also, we can investigate the chemistry of the nearby interstellar medium interacting with the outflows. If the outflows are producing some molecules here that are not observed in this direction, for example, we can map the interstellar medium to check whether the outflow is changing or the chemistry of the interstellar medium. We can also investigate the trigrade star formation in clusters. In this work in 2016, Dominelli, we showed that we found far infrared clumps at 70 microns using Herschel data around the Westerlund 1 cluster. It's one of the biggest, most massive clumps in the galaxy. And we asked then if those clumps could be star-forming regions that are being trigrade or induced by the presence of stellar winds, shocks, or any other interaction with the cluster population in here. So yeah, those are the clumps I'm talking about, highlighted right now. So we can ask what is the molecular content of these clumps, if they are forming stars or not, or if they have another nature. And this is an interesting science case for single pointing observations that we can, oh, it's raining, that we can do single pointing observations of the CO, for example, to see whether we fall in falling or outflowing activity in those clumps, suggesting the presence of star formation. Well, in summary, we can say that high mass stars is a hot topic in astrophysics. So where to look at? We have several available surveys from the infrared to the submillimeter that you can start looking at them to select the best source for your case. and they have a very good synergy between these surveys and single dish telescopes using, for example, LLAMA and APEX telescope. One particular thing for the LLAMA project is that the top 100 is a well-characterized sample of bright sources at terahertz frequencies, so they can be used as calibrators for the commissioning of the antenna. We have the properties of the source as well derived and everything. The CO is well determined. And again, the mid-JCO lines will be available from LLAMA in the first slide. So we will start with the CO65 at band 9 observations. So if you're planning to do CO observations with LLAMA, it's good to take in mind that you will have to deal with the CO65 transition. Study of feedback processes from high mass star formation is crucial to understand their impact in the interstellar medium. And yes, there is a plenty of interesting science case yet to be done. So if you're interested in high mass star formation, we can talk a lot about it. And one last thing is that interferometry is the future for this area, because we have to really dive deeper into the monsters to see what's going on at the central regions of the outflows of the sources that are expected to be high mass stars. Yeah, and yeah, that's it. Thank you very much.
Thank you, Felipe. First questions from here. Zulema, no, a minute.
Yes, you said that you wanted to study the evolution of these sources. In which stage are the ones that you are looking for?
Yes, let's go back to there. Okay, so I think it's better if you turn off the light. Wait, okay. In this plot, I forgot to mention, we have 4 classifications of the sources. We have 70 microns weak sources, so they are at the earliest stages of star-forming regions. We have infrared weak sources, so they are in a between stage. We have infrared bright regions with no centimeter emission, so those are the sources that are expected to be at the main accretion phase. And we have H2 regions with centimeter emission. So we are probing all the evolutionary stages of the main sequence phase. Mm-hmm.
Another question here. Adric.
You mentioned something about this plot that was off. Or the
yes. Here.
you were expecting the sources to fall on this Maud and Wu et al. Relations.
That's one interesting point, because, for instance, those studies were performed in low J CO lines, so they are easily excited. So you can also probe material that are not associated with the outflow itself, but it's heated in the nearby stellar medium. So you can also expect that you are tracing more material here that is not associated with the process than here. Those lines have a higher excitation temperature, so they are more difficult to excite.
Maybe it's a bit suspicious that the slope is exactly the same.
Yes.
Yeah.
Mm-hmm.
And the other question I had, the correlation between the population of the upper J levels and volumetric luminosity. What is the physical explanation of this? Is it because the higher volumetric luminosity sources tend to have higher temperatures? Or
let me move that. I think, yeah, That's it? This one or this one? Yeah, okay. There is a physical interpretation for that. So as I told you, different lines have different excitation temperatures. So we expect that higher JCO lines are being emitted in the innermost part of the stars. So we are exciting a smaller amount of material very close to the central source, while those lower J lines are excited at a larger distance. So we are probing a larger amount of material.
Yeah, but then why does this correlate with the bolometric luminosity?
Yeah, that's one point. Why it's correlated? Because the amount of material should be proportional to the heating of the source, I guess.
Okay, thank you.
Yeah.
We also have one question for the remote audience. Also Felipe, the other Felipe Alves from German, in German now, are asking, he wants to know if there is any morphological difference between the CO outflows at different transitions.
That's...
For example, size, optical depth, some morphological difference between the different COs transitions.
So Felipe, as I was telling, so the low JCO are really easily excited. So if you take, for example, the emission at 3 sigma of the CO43 map, you are probably probing a larger area in the sky than if you take a 3 sigma threshold of the CO65. So it depends on where you set your limit on the observation. In my personal opinion, I think that there are no significant difference, but I expect that low JCO outflows are indeed larger than the structure we detect in higher JCO lines.
I have a comment on that. As far as I know, the CO transition 6 to 5 is more sensible to temperature. I don't know if this can affect what are you seeing, because if you have some place that is a high temperature, you see difference in CO 6.5 you not see in CO 2.1, for example.
Yes or no. I don't know if I understood your question. We see difference in the temperature.
I know I'm saying that the transition CO 6 to 5 is more sensible to increase of temperature than the CO 2.1.
It should be. It should be.
And this cannot introduce more morphological difference because of this.
Yes. Yeah, if you think on this size, in this way, yeah, you can also explain that.
Okay, you have another question from Gabriel Hickel. Now, he asking if there is any way to relate outflow parameters to multiplicity. He said high-mass stars are in clusters, forming clusters.
Yes.
And he asked if there is any way to relate outflow parameters to multiplicity.
Well, there is if you look for higher resolution images. For example, where did I show? In some of the images in the infrared, you see several multiple outflows, not bipolar outflows. And then, of course, you expect that those multiple outflows arise from several objects in the same region in the sky. But it depends, of course, on your spatial resolution of the data. From the CO625 resolution that we have, it's about 10 arc seconds. The beam is right here. We cannot distinguish between multiplicity on the CO.
Okay, and I have a last question, more questions here. Remote audience also not?
No.
I will do a last final question, just more curiosity. You show in ALMA data, you say that you have an ALMA data, but you have you have a sample of almost 100 sources, and what exactly was the criterion to choose which one was the nice to look with ALMA?
the highest luminosity bolometric sources, so the most luminous sources from our sample, so they will be better demonstrated there, and also outflows that are how can I say? They are resolved outflows, not unresolved outflows. They should have a morphology that you can see, okay, the outflow extends in this direction or not.
Okay, so thank you again, Felipe. Thank you
you.
all. Thank you also people on the remote audience, and see you next year with a new agenda.
Yeah.